All right. I'd like to solve some problems for you. I think it helps to see problems solved in real time as someone's talking through them. And to solve these problems, I'm going to be using the kinematic equations. Now, we didn't derive these in class based on the average velocity and average acceleration equations that we already did, but I don't want to spend that much time deriving them. I do want to talk about how you use them. The first question I have for you is a swan. The swan on a lake gets airborne by flapping its wings and running on top of the water, and it accelerates from rest at an average rate of 0.5 meters per second squared. How far will it travel before becoming airborne? So what I'm going to do is I'm going to write down the information that I know from this problem. And I know that the swan must reach a final velocity of 2 meters per second squared. It starts at rest, so I know its initial velocity is 0 meters per second squared. And then my acceleration is equal to 0.5 meters per second. I'm not going to fuss too much about significant digits because we are focused on problem solving. The variable that I'm looking for is my distance. So what is my change in x? This is what I know, and this is what I'm looking for. So I'm going to take a look at my kinematic equations. I'm looking for the one that does not have time in it because we don't know how long the swan is going to be flapping its wings and running before it's airborne. We could determine how long that would be with these kinematic equations. We can also skip that step and go straight for the displacement. So this last equation is the one I need. It has final velocity, initial velocity, acceleration, and the displacement. So I'm going to write that right here. And then I'm going to put in my values. So the final velocity is 2. Initial velocity is 0. Okay. 2 times the acceleration times the change in position. I know that my 0 is 0. I can ignore that. 2 squared is 4. 2 times 0.5. Well, 0.5 is 1/2. 2 times 1/2 is 1. So I get 1 times the displacement. So my displacement is 4. So the math on that one worked out fairly nicely, and I didn't have to do a lot of rearranging. But I also want to write my answer with units, 4 meters. So that's how long or how far the swan goes before it actually takes off into flight. Okay, that was my first example. I'm going to put swan. Example 2 is going to be about a gray squirrel. So it says, consider a gray squirrel falling out of a tree to the ground. If we ignore air resistance in this case, determine a squirrel's velocity just before hitting the ground, assuming it fell from a height of 3 meters. The squirrel is in the tree, so we know that the squirrel is starting from rest. So I can put that my initial velocity is 0 meters per second. It fell from a height of 3 meters, so my displacement is 3 meters. And it says determine a squirrel's velocity just before hitting the ground. So I am looking for a final velocity. Now, it looks like there's one piece of information I'm missing, but I'm not really missing it. They're just not going to tell me. If a squirrel is falling out of a tree, it's falling out of the tree because of gravity. we actually know what the acceleration due to gravity is, 9.8 meters per second squared. We know initial velocity, displacement, acceleration, and we're looking for final velocity. So this is what we know. What we don't know is time. Sometimes it's easier to find the equation we're looking for if we look at the thing that we don't have. So right here, we don't have time, much like the last one. And so we are looking for something with final velocity, initial velocity, acceleration, and distance. Okay, so we're actually going to use the same equation that we did for our problem with the swan. Again, I'm going to put my numbers in here. We're looking for the final velocity. My initial velocity is 0 again, plus 2 times 9.8 times my change in position, and that would be 3. So my final velocity squared is going to be equal to 2 times 9.8 times 3. So I got out my handy dandy calculator and calculated 2 times 9.8 times 3, and I got 58.8. Now I need to take the square root of both sides. And I get 7.668. So I'm just going to round it to 7.7 meters per second. Again, in this class, I'm not real concerned about significant digits. Those come into play more when you're working on labs where you need to calculate a estimated error and things like that. When you're just doing problem solving, it's not as necessary. So I just rounded to one number after the decimal place, and I got 7.7 meters per second. On to example 3. I've still got the equations, my kinematic equations written down for reference. I'm not very good at remembering things, especially equations. So I've still got those written down. Example 3 is going to be about a bullet. So it says a bullet is fired straight up with an initial velocity of 333 meters per second. Okay, how much time passes? So I'm looking for t before it reaches the highest point when its instantaneous velocity is 0. Remember, what we're dealing with is a bullet being shot straight up into the air. When the bullet changes direction, that is actually a velocity of 0 because we're going from a positive velocity and then switching directions and going to a negative velocity. So in between positive and negative is always 0. I've got my initial velocity here and my final velocity here. I also know that acceleration is 9.8 meters per second squared. And they gave me a hint here. They said, use acceleration that's negative. Now, I didn't do that in the last problem, and it was because of my reference frame. I had said that the squirrel was starting at 0, and I was looking at its displacement from 0 and considering the downward direction to be positive. In this one, they give us a little hint here and tell us that gravity should be negative. Usually when you do problems, keep your frame of reference like this with negative acceleration for gravity. It will make life much easier. I've got the initial, the final acceleration, and I'm looking for time. We're not going to be using this equation because it doesn't have time in it. So I need an equation that has time. Now, this one would be fine, except we don't know distance. So I'm going to keep moving up. And the very first equation which is based on our average acceleration equation, is VF equals V initial plus AT. So I'm going to use that one. V final is 0, and my V initial is 333. And I need to solve for T. So I get 9.8 T equals 333. I move over to my calculator, 333 divided by 9. And I get time equals 33.97. So that is actually going to be 34.0 seconds when I round it. The problem didn't ask this, but I'm kind of curious. I'm wondering, how far does that bullet actually travel if you shoot it straight into the air? It travels for 34 seconds, but how far does it go? So now I have a choice of equations that I can use because I've already solved for time. I think I'm going to use this bottom one because even though I've solved for time, if I can go back to my original values, I like to do that just in case I made a mistake somewhere. I'm going to write that equation down here. My V final is 0. My V initial is 333. And I'm curious, what is my distance? How far does the bullet go up into the air? The first thing I'm going to do to figure out what's the square of 333? That's really large. The square of 333 is 110,889. And then negative 9.8 times 2 is negative 19.6. I'm going to add this term to both sides. And then I solve for x by dividing. And I get my x equals 5,657.6 meters. I tend to ask a lot of questions. I found a conversion calculator on the internet for meters to miles, and I found out that 5,657.6 meters is equal to 3.5 miles. When you shoot that bullet up into the air, it goes 3.5 miles into the air and then it comes down. So I did pause this video for a second to research how far bullets actually do travel up if you fire them straight into the sky. It seemed like 3 kilometers was a more common answer. 333 meters per second would be on the high side for the velocity of a bullet. That might be a little high. All right, I want to talk about one more problem before I end this video. The problem gives us a position versus time graph. It says, explain how you can use the graph of the position versus time to describe the change in velocity over time. Well, remember, the change in velocity is going to be the slope of our tangent line. It says, identify the time when instantaneous velocity is greatest, at which it's 0, and when it is negative. Basically, for when is the instantaneous velocity greatest, A, B, C, D, or E, we're looking for the line, the tangent line that's the steepest. So right here, my tangent line might be like that. But at point C, it would look more like that. So line A is steeper than line C. Greatest velocity equals the steepest slope. And so when is the instantaneous velocity greatest out of A, B, C, D, and E? It would be A. When is instantaneous velocity zero? A zero slope is horizontal, and instantaneous velocity will be zero when something changes directions, because the line kind of curves over like that. That is where the slope will be zero. So D is going to be the horizontal slope. So we can say horizontal slope means zero velocity. And then when is it negative? The only place it's negative on this graph is going to be at point E, because it's starting to go down. On the graph that they gave us in the original problem, it's very subtle, but E is indeed slightly lower than D. So we would look for a negative slope would be negative velocity. Okay, so here's my meager drawing with my tangent lines in it. And again, this is a calculus concept I hope you're familiar with. I'm not going to have you do derivatives and integrals to go from velocity equations to acceleration equations and things like that. But it's something that we can do using calculus as a tool. Now, before I end this video, I do want to look just at a couple of graphs. And these were related to a problem I thought about showing you, but really I just want to talk about the graphs. The top graph is a velocity versus time graph. And you could see that they've marked some tangents here. The first tangent is positive. The second tangent, or top of the parabola, is horizontal. And third tangent is negative. If we go down to the acceleration chart, we will see that they mark the same times and that we have a positive acceleration for that first time. It's a straight line, so it's constantly changing acceleration. But where we had that horizontal tangent line, that is where acceleration is zero. So as a straight line, that's when it crosses zero. And then at that third point, it is negative. So it would be negative 10 at that third point. So I just want to show you that as one more example of kind of the way tangent lines change when you have a curve. I hope solving some of these problems was helpful for you. But if you do have your own questions on the problem sets as you're doing them, please let me know and I will try to help out as best I can. And if we can't do it over email, I'm happy to meet with you virtually in a Zoom call. And I hope you have a great night. Thanks.